So in the last class, we discussed the effect of this K-space magnetic field. We demonstrate that in a semiconductor, as a particle move around in the energy band, we may have some kind of K-space magnetic field. This K-space magnetic field is coming from some kind of like a barrier space. It's because in a band, we can view electron as if it has some internal degree of freedom, like a spin. As the momentum changes, this spin actually rotates because the spin is locked to the momentum in a certain way. And certainly in the band, we don't really have a spin. This spin really means that when you have a many site per unit cell, what is the weight of a wave function on a different site on the unit cell? So this different distribution of the weight give you something like an internal degree of freedom, like a spin. But however, this internal degree of freedom always locked with momentum. As the K moves, internal degree of freedom move around. So this internal degree of freedom is described by some kind of a wave function, per psi 1, per psi 2, some column vector. Okay. And then we can have this, then using this K dependence of this internal degree of freedom, we can construct so-called vector potential in the K space using this formula. So I will come back to this. Then using this vector potential, we can do this antisymmetric derivation to obtain so-called K-space magnetic field. Just like in real space, we have similar formulas in real space, but here we do everything in K space. So the derivative is respect to K, not respect to X. Then we get a K-space magnetic field. So in general, we have this K-space magnetic field that would influence the motion of a particle. And in the last class, we did a three-dimensional version of the theory. If we do a two-dimensional version of the theory, we have a similar thing. And then we have this interesting formula that even when you have a field band, we can still have so-called Hall conductance, even without applying magnetic field. So under proper situation, if this integration of this curvature, actually in two dimension, let me do this. In two dimension, we just have only one choice, x, y. Because x, y, y equal to 0, so only non-zero things x, y, so we only want one component. So this is easy. So, and if this integration is not equal to 0, and then we have some kind of a Hall conductance. Okay, so that is basically the results. So the even field band can have a Hall conductance. Then you say, is this an insulator or metal? Because we say that if the energy band is totally filled, electron cannot move. If you apply the electric, nothing can happen. So this is a little bit strange. How come we have a Hall conductance? And so actually, what really happens is that this first, let me try to say, we have energy conservation. Because if you apply electric field, electron move in the direction of electric field, you do some work. When you do some work, that means you transfer some energy to the system. And when you have a field band, electron cannot gain any energy because the band is totally filled. It cannot do anything. So there's no way for the electric field to inject energy into the system. So that's why we believe when you apply electric field, there's no induced current. Because once you have induced current, you do work, you start to transfer energy into system, but the system cannot accept any energy because the energy band is filled. But however, here in our argument, there's a loophole. If induced electric field is perpendicular, if induced current is perpendicular to the electric field, You do not do any work, actually. So actually, in this situation, you can apply electric field, induce transverse current without injecting any currents, energy, into the ground states, into this system. So that seems okay. So how to understand this induced transverse current even when the band is totally filled? You're supposed to have an insulator. So from energy point of view, it seems okay. Energy argument allow these transverse currents. But what really happens is that we have this, let me just say that in words. What really happens is that when you have an electric field, the currents of the ground state is changed. And you know, what is the current of a field band? You know, it's really something like usually the current is that is sum of velocity. You can see every particle have a velocity. It's a sum of velocity of each particle. And if total velocity is not zero, then you have some currents. But however, if velocity is really the derivative of a function, then you can show that for the field band, the sum velocity is always equal to zero. So that's the ground states have zero currents, basically. But however, when you have a D, then this velocity receive a correction. This is the force. So this force actually is E times electric field. So if electric is not equal to zero, the velocity, the definition of velocity changed. You receive this actual term. And for the field band, for this ground state, this sum of the actual term is not equal to zero. So this is a source of this transverse current. So basically, what happens is that we have a ground state wave function. When you apply electric field, this wave function deformed a little bit. But deformed wave function as a ground state actually carry currents. So we have a very strange situation. The ground state of system can carry non-zero currents. And this is the Hall conductance we're talking about. Because the ground state carry currents, certainly the energy do not change. So therefore, the electric field and the currents always perpendicular. There is no injection of energy into the system. The ground state remains to be ground state. It just carry currents. Okay. And this current is very similar to the current in a superconducting ring. You can see when you have a superconducting ring, we say, okay, we may have a circulating current without decay. And here I want to say the following. This current is very similar because when you have a flux through the hole, the ground state of the ring have a current. It's a ground state current. It's not something moving give you a current. It's just ground state have this current. Certainly the total current actually is equal to the ground state current plus the current due to excitation. The current due to excitation can dissipate, have scattering, have friction, This is the current we usually talk about. We usually assume ground state have zero currents. But in a superconducting ring, actually, the ground state have a current. So when all the excitation dies away, you have a ground state which have a current and which flowing forever. It's very mysterious if you think some excitation have a current which kind of keep going forever. That's very difficult to imagine. It has a ground state have a current. So therefore, this transverse current induced by electric field in this kind of particular band is very similar to the superconducting currents, which is a current in the ground states. Even without any excitation, we can have some current. So that is of this nature. And this current also always do not induce any energy. There is no energy transfer. Okay, so that's the first point. And the second point is that this quantity actually is quantized as 2 pi times integer. I try to explain why. Okay, why this like 2 pi times integer. Okay. So first we have to understand what the C really means. Remember, this C really means the following. Suppose we compare the phase of the states at a different k. So we say, okay, if we compare the two vector at different k, and these two vectors are slightly different. So we say that actually there may be a small phase here. But this small phase, actually this delta phi, actually is equal to this vector potential Ci times delta Ki. So this is how we define it. This kind of vector potential in K space have a more physical interpretation. It's actually produce the phase difference when you compare two nearby states. What's their phase difference? Their phase difference actually is this vector times a shift of a k, and that gives you the phase difference. So that is precisely this meaning. Then what the D means? The D means the following. Suppose we have a dxy, sorry, and we multiply this delta kx, delta ky, and this quantity also have a very geometrical meaning. Okay, it's like a curl. The curl is following. So let's consider this square delta kx, delta ky. Okay. Then we say that from here to here there's a phase difference. There's like a delta phi 1. So let me just write it. There's a delta phi 1, and here to here you have a delta phi 2. And here you have delta phi 3, you have delta phi 4. Okay, you try to compare those phases, go through a small loop. And you say, actually, when you go through loop, this phase, the total phase difference should be more or less 0. Because of the following, you can see from here to here you have a phase difference. Compare these two states, you have phase difference. But compared to these two states, you have almost the same phase difference, but in the opposite direction. You compare them in the opposite way. So these two phases almost have opposite sign. They almost cancel each other. And these two phases almost cancel each other. But not quite. They're slightly different because this phase difference here, this phase difference here, so they're at different place, they don't quite cancel each other. So because they don't quite cancel each other, so when you go through this small loop, compare all these phase difference, then this total phase difference is exactly this quantity. And this curl actually is really, this derivative really try to compare. So this is a phase difference, and this say in x direction, and this derivative in y direction. They try to compare the phase difference of a difference of phase difference in y direction. So that's a physical meaning. So therefore, this integration have this meaning that if it goes through a small loop, the total phase difference you'll get is this. Okay. So this is very important. So with this understanding, we can understand what is suppose we integrate over this dxy in some area. What this really means. Okay. So actually, this integration means the total phase difference around the loop. We're just using Stokes theorem here. Suppose we start from here. We have phase difference delta phi 1, delta phi 2, and etc. Delta phi 3, and etc. We go through this loop. Okay. We ask, what is total phase difference? And this can be obtained by saying, let's go through a small loop. We go through this small loop, go through this small loop. But all these internal loops have a shared edge. They all cancel each other. So you can show that the sum over all the phase difference around the small loop became the total phase difference or cumulative phase you get around the boundary of the whole disk. Okay. So therefore, this is a phase difference. Let me just note it. This phase difference go around the whole loop. It go around the whole loop, we get a phase difference, and this equal to this. So this is remarkable because we want to compute the phase difference around the loop. And one way to do so is that we extend the loop into a disk. Then integrate this integrate d on this. So actually, this phase difference on loop actually is equal to this loop integral for dk times c, this phase space vector field. If you integrate this vector field around loop, you get total accumulated phase difference. And this phase difference, this loop integral along the edge can be expressed as a surface integral on the disk. And these two are the same. And using this result, I can show that this one is quantized. Because suppose, let's consider on the sphere. Suppose our K space is a sphere, S2. Okay, let's pretend that. Then we can consider an integration of this vector around the loop. Try to compute the total accumulated phase around this small loop. Then we can do this using Stokes theorem. We can extend this loop into the disk and do the integration over d on this disk and obtain this curl, this circular integral. But on the sphere, we have another way to extend this loop into the disk by going outside. So we can integrate outside and to get the same results. Then here is a thing. The two results would agree because they compute the same phase. And the two results agree if there's a sign difference. If the integration inside and the integration outside, let me see, they add up to 0. Then that's what we agree. But there's another choice they agree. If they add up to 2 pi, they also agree. Because total phase accumulation of 2 pi is the same as nothing. So therefore, because of this, this quantity has to be 2 pi times integer. Otherwise, we cannot interpret it. We cannot interpret this integration of d on disk as total accumulated phase around the edge. But from definition for d, such a d indeed have such interpretation. The integration of d on the disk is a total accumulated phase around the boundary of the disk. This is geometrical meaning or geometrical meaning of this d. Because d has this geometrical meaning, so therefore their integration on any closed surface has to be quantized as 2 pi times integer. So that is so this is actually the mathematician, the Chen got this result, but you certainly use a different language. And but this is we get quantized d. And so this quantization of d is quite significant because it means that we have a different insulator. Remember that if an energy band is totally filled, then we get something like insulator. Okay. And but usually when we say insulator, okay, insulator just insulator. But now the insulator became rich because we can have a different kind of insulator. Because some insulator, this integration is 0. Other is not 0. Yes.
Sorry, it's not clear for me the argument that you make here with the sphere. I know that the two phases must add up to integer multiple of 2 pi.
Yes.
Why does that imply that the phase itself has to be an integer?
No, phase is not integer. This total phase is 2 pi. Okay, let me go through. I'm a little bit quick here. So basically, this integration of the d inside and the integration of d outside should equal up to 2 pi. Yeah, in order for the picture to be consistent. Okay. And but if d inside and the integration d outside they are equal up to 2 pi, what do you mean by their sum is quantized? But actually, what happens that this total integration of d is not the sum of the contribution from inside and outside. It's a difference from contribution from inside and outside. There's a strange thing about orientation. Because I think there's a right hand. Because here the edge go like this. Okay. So when you do the d, the surface have orientation pointing outside the sphere. And when if you're using the integration outside to represent this curve, they have different rule. So actually, you have to assume this orientation of surface have arrow go into the square. And this kind of integration, their sum has to be these two integration has to be equal up to 2 pi. But however, in this case, the orientation for the outside is different. Both inside and outside which assume the same orientation. And so there's a sign change. So before these two integrations are equal up to 2 pi. And when you take a sign change, that means so this quantity actually is a difference of the contribution from inside and outside if you have opposite orientation. And because if inside and outside have opposite orientation, their contribution is the same up to 2 pi, then their difference will be multiple of 2 pi. Yeah. So there's a slight change of orientation. But at the end is we get this result, 2 pi times integer. Okay. And then I want to emphasize that this quantity is a property of the band. It's a property how this wave function changes as k shifts. So once you have a band, for every band, you can compute the d. You can do this integral. For every band, you can assign this number. It's called train number. So this band may have a train number equal to 1, and the next band may have a train number equal to -1, and etc. Okay, so you have this, for each band you can assign a train number. Okay, and when you fill that particular band with different train number, you get an insulator, but you get different kind of insulator. And those insulators would have a different Hall conductance. So that is that's what we call the train insulator. It's coming from some kind of topological property. And so you may say, okay, this should be called this topological insulator, but this is not topological insulator. This is a train insulator. The topological insulator describes something different, and so actually the train insulator is more topological. In the following sense. So let me just make some comment. What do you mean by different insulator? So what do you mean by different insulator? So different insulator really means the following: is that suppose we have this we have a Hamiltonian H1. Then it's a train insulator with a C equal to 1. Okay, that means a band with a train number 1 is a field. And then we have another different system where the band is filled have train number 2, so the train is equal to 2. So the question is that can we deform this H1 into H2 without phase transition? So basically, it's that can we change the train number band continuously in some way? And we say we cannot because this is quantized. But actually we can. You need to pay a price. So actually chain number can change. If when you do the deformation, this two band, these two bands getting closer and closer, and they touch. When they touch, then the states here will get mixed. Okay. And then if these two bands have different chain number, then the chain number may get mixed. Okay. If you continue to deform the Hamiltonian, if the energy gap open up again, when they open up again, it's not guaranteed that the chain number of the two bands remain to be the same. They may change. Actually, they may change. They may both change. This may change to 0. This may change to 0. The total chain number of two bands is not changed, but they may chain number can transfer from one band to another band when the two bands touch and mix. But when two bands touch, that represents the phase transition, because before this ground state have an energy gap, because if a band have energy gap, if the first lower band is totally filled, to create any excitation, you have to move an electron from lower band to upper band, and you have to cause energy delta. So this is a particular state we call the state with energy gap, very rigid states. They don't do anything. But however, if you deform your Hamiltonian, you close energy gap, then things can happen. Then chain number can mix and transfer. And when the gap reopen again, what left behind as a ground state may become another type. Okay. So the point is that from here to here, it can happen, but however, it is through a phase transition. So this is gapped. And this also gapped. But there's a gapless point in between, and that means phase transition. So this really became a picture that the chain insulator with different chain number belong to different phase. And to go from one phase to another phase, you have to go through this gapless point, and that is a phase transition point. And so that's why it's very interesting. Yes.
What if instead you just tune the chemical potential so that a higher band gets filled, and you just add the neutron number of the band?
And that's also gapless, because when you're changing chemical potential, if chemical potential between this gap is a gap, the ground state gap. Once chemical potential reach here, this band start to fill, you create a small Fermi pocket here, and this small Fermi pocket would have a gapless excitation. If you bring chemical potential back down again, Fermi pocket disappear, it becomes gapped again. So if that process corresponds to the following, you have a transition, but you have a window which is gapless. Yeah. But there's no way to go from here to here without closing gap. If you don't close gap, it will be smooth change. That would be smooth change. And if you don't close gap, these two chain numbers do not change, so you cannot do that. But however, yes. Yeah.
So I'm just wondering why the total chain number is remain the same.
Okay. Yeah, the total chain number is the same. How do I understand this? It's kind of like let me do this way. Suppose we fill two band. Okay, I'm giving a physical argument. If you fill two band, okay, then you have a Hall conductance, which is contribution from both band. So actually, this Hall conductance is given by the sum of the two chain number. Okay. Now you do this. You try to mix these two field band. But when you mix two field band, this empty band and the field band still have a gap. So nothing. So the energy gap actually do not close. Energy gap do not close. We will try to mix this. And if energy gap do not close, this Hall conductance cannot change. Yeah. And so this is why we say, if you mix these two bands and reopen them again, the chain number may distribute differently, but total chain number is the same because this gap do not close. To change the total chain number below the energy level, you have to close this energy gap at this energy level. But I didn't give you an explanation, I just give you a plausible reasoning. And you can prove this. But this is not what I'm going to do here. And but I will make comment is that my following comment will relate to your question is that actually this picture is not rigorous or not even proper because this is a free electron picture. We say that if you do not turn on interaction, there's no way to go from here to here because we're using this free electron energy band to obtain this picture. So there's a much more profound question. If you allow interaction, can you go around in some higher dimensional parameter space, return interaction, and go back to the free, and then without closing gap and change this chain number? Yeah. So the answer is no. So actually, that argument really says that as long as you do not close energy gap, even when you turn interaction, this chain number is topological. But not in this expression. When you have interaction, this expression no longer valid. This expression really is for free electron. But the chain number itself, Hall conductance itself, is more robust than the free electron picture. Even interaction, even when the free electron became invalid, this Hall conductance is still there and still quantized. So this requires understanding why Hall conductance is quantized for interacting system. So you cannot understand that using free electron picture. So this will be it's kind of very different situation. And yeah, maybe in the more advanced class, when you do many body theory, you may encounter this issue. Yes.
I'm a little bit confused where when you went to the form 100 into another. So the Chern number is a topological invariant, right?
It's topological invariant for the free electron system because the concept associated with energy band. Energy band is concept of a free electron system. So therefore, within the one free electron picture applies, you can have energy band and you can define chain number. When you have an interacting system, you don't even have an energy band. The whole picture is different. Everything is destroyed. We don't even have we don't have PIRSA. We have nothing. There's nothing there. So therefore, one has to understand the interacting chain number. Sorry, one has to understand so in interacting system, we don't have chain number, but we can have Hall conductance. You have to directly understand why Hall conductance is quantized. So for interacting system, we don't even talk about the chain number, but we talk about Hall conductance. But at the end, there's a chain number pop up for the different reason. Yeah.
However, so when talking about the electron picture, can I have different Chern numbers, and those different Chern numbers would correspond to what?
Different chain number correspond to different phase of matter. Because when you fill that band with different chain number, then you have different chain insulator. And at least here we show that if you do not turn on interaction, those different chain insulator cannot be connected. I just say without turn on, within the free electron picture, the only way for chain number to change is to close energy gap within free electron system. And here I want to make a claim that This is much more robust than that. Actually, even for interacting system, as long as you do not close energy gap, this Hall conductance is remain quantized. So therefore, those free electron system with different Chern number cannot be connected even if you turn on interaction. To prove that one use different picture.
Just to get a little bit of insight on that, when you calculate the Chern number, in this case, the Chern number of the K-space, right?
Yes.
So what you're saying is basically that there's no way that I can change the topology of your K-space by switching on interaction.
No, it's not that. I think to answer this question, let me explain. So first, I want to say that once you turn interaction, there's no K space. There is no Brownian zone because the point is that the wave function is complicated. You cannot using this single particle filling energy picture to understand the ground states. So the whole picture breaks down. So yeah, but however, to understand this Hall conductance, so why Hall conductance quantized? What one considers is one put our system on the torus. Put your whole system on the torus. That's your ground states. Then what you do is that you try to insert electric flux. Here you have a phi 1, and here you have a phi 2. Not electric, magnetic flux. You try to insert magnetic flux in these two holes of the torus. Okay. So then what you find is that the total ground state, this many-body ground state wave function, became a function of phi 1 and phi 2. If you have different flux, the wave function changes slightly. Okay. So now here I'm going to fly. And first we notice that phi 1, phi 2 live on the torus, another torus, because the phi 1, phi 2, if you 0 flux and 2 pi flux is the same thing. So therefore, this function is a periodic function of a phi 1 with a period of 0 and 2 pi. And also periodic function of phi 2 with a period of 0 and 2 pi. Okay. So therefore, we can view this, now I'm flying, this wave function as a fiber bundle on the space parameterized by phi 1, phi 2. Basically is that on every phi 1, phi 2, I have a particular ground state, like I have a fiber. And here we have another ground state, many-body ground state, another fiber. And then, because ground state is a one-dimensional vector in some big Hilbert space, and as you move around, this ground state may change in space. So this became so-called a fiber bundle on the torus. And then that's what the chains work. They say, how many different kind of fiber bundle can you have? Let's describe this twist. Actually, you can define similar twist. Let's call this a C tilt I using this many-body ground state wave function, phi 1, phi 2. But now you do d phi I, phi 1, phi 2. Okay, so I'm changing my notation. Okay. You can define some kind of vector potential, but in this phi 1, phi 2 space, using similar idea, this barrier space. And then this barrier space may have a quantized curvature of magnetic flux, but in the phi 1, phi 2 space. And that one should be quantized. You can show this one is a quantized if energy gap of many-body wave function do not close. Yeah, so this gave you a many-body way to prove this quantity is a topological. But this topological really means that against any perturbation to the Hamiltonian, you can change the hopping, you can change interaction. No matter what you do, as long as you don't close energy gap, this Hall conductance is quantized. It's very robust. So this is amazing. So this is So this is really the essence of a quantum Hall effect. Because this is many body Chern number. So this band is a single body Chern number. It's a Chern number coming from the twist of this like 2 by 2 the 2 column vector if you have 2 band picture. But now we create a twist using phi 1, phi 2 of a magnetic flux on the torus. Using the many body wave function, we can do a similar twist, and then we get a similar Chern number, but in this many body sense. And it turns out that this many body Chern number is exactly the Hall conductance, the measure of Hall conductance physically. Yeah. So this is how we understand it. And then there's even more surprise here. You can see when we do this, I can turn interaction, but I keep one thing. I keep the conservation of a particle. The particle number conserved. So the currents can be defined. So we can have a Hall conductance. So here it looks like these two states are different if you have U1 symmetry. And because we are using the Hall conductance to characterize it, we need the U1 symmetry. We need this particle number conservation. So therefore, what I said is not topological in the sense if you add all kind of perturbation without breaking U1 symmetry, then these two are different. So now I want to ask, if you add a perturbation which even break the U1 symmetry, the particle number is not conserved anymore. Is these two states still the same or different? And this became a very interesting issue, because we can no longer use Hall conductance. There's no Hall conductance use because the U1 symmetry is not even conserved. You cannot define currents. And then I claim that even without U1 symmetry, these two still are different. But the argument for that would be much more difficult. And but I just want to say one thing, and I won't go into that. Is that this kind of quantum Hall states, when we consider quantum Hall states, or this Chern insulator, let's call it Chern insulator. When we consider Chern insulator on the disk, there is a gapless edge excitation. There's a gapless edge excitation. And this gapless edge excitation survives interaction, perturbation, even the perturbation which break U1 symmetry. And so this is a robust feature of this Chern insulator. Their gapless edge excitation survive any perturbation, even the perturbation which break U1 symmetry. So when you break U1 symmetry, we have to tell whether this state is trivial or non-trivial to see whether you have a gapless edge excitation or not. Then you may ask, why we have such robust gapless edge which survive any perturbation? We cannot destroy them. Indestructible gapless edge excitation. And the reason is that this very recent work is that this gapless edge excitation have something so-called gravitational anomaly. So it's have a gravitational anomaly because of that reason, so it cannot destroy it. So therefore, that's another way to look at this whole topological state. So this is one example of topological states. That in the bulk you have energy gap, nothing happens at a low energy. But the boundary of topological states have some interesting feature. They are usually anomalous, or not usually, they're always anomalous. Almost definition. The topologicalness in the bulk implied anomalousness on the edge. So that's a different way. So now we have a new, so by understanding the topological property of the bulk, we have a new way to understand anomaly. So the topological states, the boundary of topological states always have some anomalies. And this anomaly is direct reflection of something non-trivial happening in the bulk. So this is the simplest example this happened. And this one have a topological anomaly because for those who may know it, is that this edge state is a chiral fermion. The fermion always move in one direction, only move in one direction, not the other direction. And this kind of fermion is known to be anomalous. And if later you encounter something like a gravitational anomaly, some simple example in 1+1 dimension, you will see this example. And this quantum Hall, this chain insulator would have this anomalous edge. And because this anomalous edge make this edge indestructible. Unless you make a change of the bulk. Only when the bulk have a phase transition, this gapless edge can disappear. So this gapless edge is protected by the whole bulk feature. So that is a picture. Okay, so this is basically is some kind of a physical discussion of these very interesting states. Is there any questions? Yes.
Sorry, back to this simple example, because when the gap closes, the Chern number comes from all the little phase differences.
Exactly.
So what you're saying is when the gap closes, one guy could flip over to the other gap, switch its phase, and then go back.
Yes. The things that this. Thank you very much for this picture, for this question. Okay. So you can see here, as a changing k, this internal phi just twisting around. And then, but on the top band, they're also twisting around, but actually in the opposite direction. Suppose we only have two bands. So this vector is a two-component vector. So actually, if for the fixed k, these two directions form orthogonal basis in this really ideal state of this MK matrix we derived. So they are orthogonal basis, and these two vectors are orthogonal. So if using spin, it means if using the spin analog, means the spin in the lower band always opposite to the spin in the upper band. And then we know that this geometric phase can be using spin language. Can be when the spin twisting around on the sphere, the tip of spin enclose a disk, and the solid angle of this disk happen to be the accumulated phase of twisting this spin. Now you can see that in the lower band, the spin twisting one direction when you go around a small k loop. But for the same small k loop, for the upper band, the spin is opposite. The spin would twist in the opposite direction. So if you add these two contributions from these two, they actually cancel. Yeah. So when they mix together, and so that's why the total contribution equals 0. Means if you consider contribution for both of them, there's no contribution. So no matter how you mix them, they just always equal to 0. But only when you try to separate these two, you make a non-zero contribution. But how you separate them depends on how you open up gap here. So this is really became a way to produce this topological chain insulator. Is that you can start with a graphene, have a Dirac fermion, and here that's like a critical point. Then you can add a little bit of perturbation to the hopping to try to open up a gap here, try to gap this Dirac point. Yeah. Then you try to resolve these two. But the different way to resolve this, you can get different Chern number. And so here, by doing perturbation, you can go from one state to another state. But these two states are separated by this Dirac point. So you can imagine you have a state, they have band with the Chern number 1. It's very close to Dirac point like this. And then you close the gap, you get Dirac point. When the gap reopen again, after reopen, you may be reopen in different way. Then after reopening the gap, the Chern number in the lower band may change. But all the changes happen near the Dirac point. So by studying the neighborhood Dirac point, you can understand how Chern number change around. So that's a very nice trick, without doing this band structure calculation. That is too tedious. Okay, so here we just describe some physics of this chain insulator, and let me make some comment how to make it. So I already described how to make it by consider this starting from direct point and try to open that gap in different way. And here I want to describe another way you can see why you have chain number, not chain number. Remember, let's consider 2 by 2 matrix. Remember that if you have like a graphene, you already studied. In a graphene, we have 2 sides per unit cell. Then when you calculate band structure of this graphene, at the end you obtain 2 by 2 matrix, which is a function of k. And then for every k point, this 2 by 2 matrix give you 2 eigenvalues. Okay. Then for different k points, you have different eigenvalues, so they may get 2 curves. When you diagonalize this 2 by 2 matrix for every k point, you get 2 curves, you get 2 band. And so that's like the 2 band picture. So now I want to ask a question. How do you know whether the lower band have a chain number equal to 1 or not? How do you compute the chain number of the lower band? Certainly it's determined by this 2 by 2 matrix as a function of k. If you know this, you know that. But how to see the connection? Well, there's a simple way to see the connection. In that for 2 by 2 matrix, we can always expand as something like some kind of a C0, like identity, let me call it N0, some identity operator. And there's Ni and the Pauli matrix. Okay, we can always expand like this. Okay. And so if you have an energy gap, then that means that okay. Now here I want to say, suppose N0 is constant. Let's suppose N0 is constant. If N0 is constant, this just add a total energy shift. Okay. And then the eigenvalue of this matrix is very simple. It's just it's a plus or minus absolute value of this n vector. So this Ni form a vector, 3-component vector. So if it's constant, so this is constant, then the eigenvalue of this combination just plus or minus of this n vector. Okay. So if this Ni vector is non-zero, we have 2 bands which are always separate. Okay. Then with this picture, we can immediately obtain obtain chain number by saying that, what is this n vector as a function of k? What is this? This actually is a mapping from torus, which is a k space. Boolean zone k space in 2 dimensions. I'm doing 2D case now. In 2 dimensions, it's actually torus. But this n vector is a kind of in the it's a point in the 3-dimensional space. That's n vector. But we require energy gap. That means this absolute value n vector is not equal to 0. So that means this n vector never equal to 0. So this the origin is a whole is never 0. Then we have our interesting situation. Whether this torus would wrap around this point or not. In one way, one mapping is that this torus, through this mapping, became a torus like this here in the 3-dimensional n space. You can see this one just do not wrap around the 1. Okay. Then you can imagine that this torus may map into something like a sphere, which wrap around the 1, then with a handle. Okay, let me draw the sphere first, then I draw the handle. Torus is a sphere plus a handle. Okay, you can imagine this torus map into a sphere with a handle. And this sphere wrap around this 1. So that's like a winding number, a wrapping number. So when this torus have this non-zero wrapping number, then that's when you have a non-zero chain number. If you wrap around the once, chain number equals 1. If you wrap around the twice, chain number equals 2. So you have very direct relation. Okay. So this is how we see once we get this 2 by 2 matrix, then we can see whether the lower band have a chain number or not by consider this wrapping. Yes.
Question. So you said that in here the case space is a torus, we have periodic boundary conditions at the beginning, right?
Yes.
All right. So we're trying to describe only the bulk of the sample, or what happens in the bulk.
Yes.
So in order to do that, I can choose different types of boundary conditions, right? Or different types of geometries. In this case, you choose the torus, and it's very convenient because in here you have non-zero chain numbers. But
So in order to obtain the Boolean zone in the K space, the real space sample need to have a periodic boundary condition so that the K is well-defined quantum number. Yes. And so I'm sorry, there's many torus here. So first we have with the real space is torus, so K is well-defined. And then that's led to the Boolean zone in K space. And K space also torus, Boolean zone also torus. And so here I'm describing this Boolean zone torus, how they map into the N space. N space is described this 2x2 matrix, and whether you have a wrapping number or not. So from here you can directly see.
Okay. However, if I don't choose periodic boundary conditions in the real space,
We don't even have a Boolean zone, so whole thing breaks down. And actually, that's very suggestive. It means something bad happens. So what happens is that you can see when you have a periodic boundary condition in the real space, you have a band which have a gap. When you have an open boundary condition in real space, there's a gapless boundary states. Actually, there's something in the gap which live on the boundary. So I think the next week you'll hear this. I will not talk about edge states. I've already talked a little bit, but so this is a really strange insulator. For the closed space, there's full gap. When you have a boundary, you have a gapless edge state on the boundary, which is indestructible. And but certainly when you have a boundary, this whole picture breaks down. You don't have Boolean zone or K space. It's hard to say what is this. And so that is that's the thing. Okay, so this is how we see how we compute the chain number. But certainly, if you don't see that, you can always compute the CI, then do the integration numerically. Yes?
And what if we have M as a 3x3 matrix?
Yeah. If
think about some vectors that have spheres.
Yeah. So if N is a 3x3 matrix, then things are different. So I don't want to talk about this because okay, I can talk about that the following way. Then I have to use this, but certainly this picture no longer works. Yeah, and but the C can still defined, and yeah, I don't have a good picture. If N is a M is 3x3 matrix, there's one way to say the following. So we have 3 band. Okay, we fill the lower band, and so you can. Yeah, this picture may not always work. What I try to say, sometimes you may just isolate these 2 lower band and pretend it's 2x2. But sometimes it works, sometimes it doesn't work. And this works only if the top band have a chain number equal to 0. Then you can constrain this lower band. But sometimes top band have chain number 1, the middle band have chain number 0. Then you have to constrain these 2 bands to see this picture. But in general, for 3x3, it's more complicated. But I don't have this simple picture anymore. Yes, you have a question? I see. Yeah, but yeah, unfortunately for 3x3 matrix, we don't have a simple picture. Let me put it this way. Okay, so now let's try to using the remaining maybe 20 minutes. So let's try to have a more general theory of this. Basically, the theory we described actually works for 2 dimensions. So can we have something for any dimension, like a 3 dimension or 4 dimension? So what's going on? And so what I'm going to describe actually is a K theory developed by Kitev. which kind of classify this train insulator and also many other insulator like topological insulator. And so certainly I will only introduce case theory for the case of a train insulator. I will not talk about topological insulator. And but however, using this train insulator as an example, you can understand some flavor of the argument. You know how a different way of thinking. The way of thinking is very different from this band picture. You know, it's very different from this picture. It's totally different way of thinking. So let's start with d equal to 0. 0 dimension. That's very, very simple. In the 0 dimension, what is the insulator? Here by insulator, I mean something with energy gap. So as long as you have energy gap, then you feel the lower energy level, you get insulator. So insulator means something with energy gap, you just feel anything below the gap. So that's the insulator. Then when d equal to 0, then we ask, how many different insulators do we have in d equal to 0? Okay, what is that question? Okay, so let's think about it. So let's consider two-level system. Even simpler, we have two level, just two energy level. Then we say, how many insulators do we have? We have a two-level system with a spinless fermion. You say, okay, maybe we have a 3. So why we have 3? So the first insulator is a state where we have no fermion. So that's the insulator. Or we have the first one is occupied. Well, there's energy gap here. So that's another insulator. The third insulator we have is the two band both filled. So we have a 3 insulator, okay, for 2 level. Then second I say, okay, how many insulators do we have for 3 level? Then for 3 level, we have if you do the similar counting, you have a 4. When you have n level, you have n plus 1 insulator. Okay. Just different way to fill this level. Okay. And that's pretty simple. And amazingly okay. So therefore, in the 0 dimension, the insulator is classified by how many level are filled below the chemical potential. And because particle number is conserved, when you're doing deformation, this number of level filled or number of particles always fixed. It's conserved. You cannot change them. So naturally, it's labeled by this integer n. It's the number of field level. So therefore, for d equal to 0, we have many insulators, and it's classified by n which belong to this integer set. So that's a very simple picture. Okay, and this is the thing we want to think about. In higher dimension, we should think about similar thing. Is that suppose in higher dimension we have some kind of Hamiltonian, a very messy Hamiltonian, but we know that this Hamiltonian gave us many energy levels, but there is a gap. We want to fill this energy gap fill LO below the gap. And then we consider whether two such Hamiltonian can deform each other or not without closing gap. If they can continue deforming each other without closing gap, these two insulators belong to the same class. If not, they belong to a different class. So how many classes do we have? So really this kind of thinking. So now let's do this kind of thinking in 0 dimension. Let's see what we get. So in the 0 dimension, what is the canonical form of the Hamiltonian which have energy gap? Well, suppose let's consider a 0 dimensional Hamiltonian which have many energy levels and also have a gap here. Want to fill this. Okay. So we can see that without losing generality, we can deform all the energy level below the gap into -1, only the interval above the gap into +1. You can massage the Hamiltonian to do the deformation. And this any gap never close, we still belong to the same class. Because here we only interested in the class. So without hurting anything, we can assume we can collapse all the level into -1, +1. So then we say, how many Hamiltonian whose eigenvalue is +1, -1 of this type? How to classify this kind of Hamiltonian? How they connected or not connected? Well, in this case, it's simpler. Well, the Hamiltonian will be equal to this. I is a L by L matrix, and the -I is M by M matrix. Well, the Hamiltonian of this type certainly have this kind of spectrum. But in general, the Hamiltonian can be more general to have this spectrum. More generally, we can put this L plus M by L plus M unitary matrix. We can do this rotation. Okay. We can just rotate them. We'll do unitary rotation. This Hamiltonian remain to be Hermitian, but however, eigenvalue remain to be +or -1. Okay. And this is the key. Actually, this is the key. So here we want to construct the space of a Hamiltonian which have a gap. We just say, what is the most general space of a Hamiltonian with a gap? And we ask whether this space is connected or not connected. If the space have a different disconnected component, then this gap Hamiltonian cannot be deformed into that gap Hamiltonian, though they belong to different phase. So we have different class. However, if the space is connected, that means that every gap Hamiltonian can be smoothly deformed to every other gap Hamiltonian. Then that means we only have one phase, one class. So literally, this is this line of thinking, and this is the way we construct space. And so we assume Hamiltonian have eigenvalue +1, -1, and then any Hamiltonian with this property would have this form. Okay. So therefore, the space of a Hamiltonian, let's call it C0 in some way, is labeled by really U. Let's call this S. Sorry, U L plus M is described by this matrix. For every matrix, we get a Hamiltonian, and that's one point. So the whole space Hamiltonian with energy gap is given by this space of a unitary matrix. That's nice. But this is not quite correct, actually. Because if this unitary matrix is a block, have this L by L block, then this unitary will apply to this, just don't do anything. So therefore, this one is not one-to-one label. Many different unitary matrices actually label the same Hamiltonian. So it's a bad label. So let's remove redundancy of labeling. So if this unitary matrix differ by this unitary matrix of L by L block, Hamiltonian don't change, and that's redundant label. So I have to mold out this U L by L, describing this upper block. Similarly, there's a redundancy due to the lower block. We have M by M unitary matrix, also have redundancy. So I have to mold out the U M by M. Okay, so this is a space. This is a space. So this is the space of the Hamiltonian, which have this which have a gap. Okay. And this space is in the mathematics. There's some very nice name for this space. I want to say that this space is connected. Actually, they are totally connected. Everything connects to every other point. So therefore, there's only one class of Hamiltonian with energy gap. Looks like a trivial. Except that here we made an assumption. We assume there's a L plus eigenvalue, M minus eigenvalue. We made this assumption. And this transformation cannot change this fact. So what we construct is just one component of a gapped Hamiltonian. For this particular choice of L and M, there's many components. So the whole thing is a union of this L and M. You know, we have add them up. It's a union of L and M. And each component is connected. So that's just give you it's one thing. But the different union of L and M give us this label N. Okay. So therefore this so here I won't be rigorous, but mathematically we say that the union of this space, if I consider pi 0 means C0, the pi 0 0 we say it's a Z. It's just components. But certainly here we take a limit which L go to infinite limit and M go to infinite limit, and you get something. And but certainly right now I don't know how to make it rigorous, but I just want to say that physically it's pretty clear that how many level of field is a different class. So class is labeled by N. But the mathematicians have a fancy way to say that there's some space like this called classifying space actually. And you can take L go to N to limit, and actually the disconnect component is labeled by integer Z. But anyway, so this is a very complicated mathematical description of this very simple problem. You know why you need to go to doing classifying space once you understand physics like this. But certainly, by going through this very fancy math, you can go to higher dimension. Really, same logic can apply to higher dimension. You can obtain the classification of a gapped face in all dimensions in one shot. So that's why we go to this very fancy math. But in 0 dimension is overkill. But we understand what's going on. Okay. So to prepare for the higher dimension, so I want to just go one step further. We say this actually is a C equal to 0. So this really means that we have another classifying space called C1. So we have a sequentially classifying space. So over there we just describe a C0. So what is C1? Okay. C1 is the following. In the C1, we introduce a gamma 1 whose square equal to 1, a some matrix. And we somehow magically require that our Hamiltonian to be anti-commute with gamma 1. We just assume that. Okay. So then we do the same thing. So this is like constraint. You know, before over there, we just want to classify the Hamiltonian which have a gap, no other constraint. Now here we do the same thing. We want to classify Hamiltonian with a gap, but with the subject another constraint which this Hamiltonian anti-commute with gamma 1. Certainly, we do the same deformation. We say h squared equal to 1. We say the Hamiltonian have eigenvalue plus minus 1 because we can collapse energy. We do the same trick here. So we really classify, so over there, what we do is that we classify Hamiltonian whose h squared equal to 1. Hermitian operator, Hermitian matrix whose square equal to 1. That's what we did over there. That's a C0. Here we do the same thing. We want to classify the Hermitian matrix whose square equal to 1 and the subject is additional constraint. This space is we call C1. That's it. So what is space of C1? So the C1 space actually is a, so let's choose gamma 1 equal to identity matrix. If you do this, it's no good because this one have no solution. Okay, so therefore the choice gamma 1 is a little bit funny. We cannot choose this gamma 1 arbitrarily. You have to choose some more non-trivial case that this have a solution. Yes?
You said that H and gamma 1 commute or
anti-commute. Yeah, this is anti-commute. So there's a minus sign here. So gamma 1 is not a symmetry. It's very strange. It's a, you know, if they commute, it can block diagonalize. So the whole thing became same thing. Yeah, but it's anti-commute. Things became very interesting. So this is really the magic. Undefined is the magic. Okay. So the so we have to choose the gamma 1 equal to the sigma x cross I. This I is some kind of n by n matrix, some big matrix. Okay. Then choose gamma 1 to be this. And if you choose gamma 1 to be this, then we say, okay, these have a solution. So the Hamiltonian can be, it's very simple, can be sigma z cross something like this. I n1 cross n1 minus n2 cross n2. Sigma z can be this. Okay. But this is just one special case. So then you can see that we can obtain the more general Hamiltonian, which is square equal to 1 and anti-commute gamma 1. This anti-commute because this sigma s anti-commute sigma z, and I commute with any matrix here. That's why they anti-commute. And we can do rotation. And imagine we can, but the rotation we can do is limited. We can only do the following rotation: minus I, then we got sigma 0, sorry, cross this b n by n, and another rotation is minus I sigma I cross A is n by n matrix. And there is some similar rotation. It's a Hermitian conjugate on this side. So this is the two unitary rotation we can do. You say, why you can only do these two rotations? You cannot do the other rotation. Because these two rotations keep gamma 1 invariant. This is the key. If you do this rotation to the gamma 1 do not change because the sigma 0 and the sigma x both commute with the x in the gamma 1. So actually, gamma 1 do not change under this rotation. So that's guaranteed that we're using this rotation to deform a Hamiltonian. This new Hamiltonian have the same commutation relation with gamma 1 because gamma 1 do not change under this rotation. So therefore, the new Hamiltonian still anti-commute with gamma 1. If you do some other arbitrary rotation, the new Hamiltonian may not anti-commute with gamma 1. Okay. So this is our thing. And there's another point I want to say that actually this rotation is quite interesting. This rotation. Okay. And we can use this rotation to we can choose this A to some way to flip sign here, actually. So because of time, I will not go into this. If you think about it, you can use one rotation to flip sign here. This sign can be flipped. So actually, we don't have to consider these two blocks. Since this sign can be flipped under this rotation, so we can just consider the one block. So the whole thing is just I n by n is fine. Okay. So this is we can consider just that. And also when it's I n by n, then this rotation actually commutes through this. So again we have similar situation. This is space C1 is naively is U n cross UN. Naively is this. You have two n by n rotation. But however, one of the rotation don't do anything. So we have to quotient out one rotation, UN. Okay. And that's it. We don't have this component because this L, N1, N2 just all collapse into 1. So this whole thing, there's no union. And this one is connected. So pi 0 C1 equal to 0. Only one component. There's no other component. Okay. So Then what is C2? Okay. And C2 is for the C2, now we have a two gamma matrix. Gamma 1, which anti-commutative is H. And we have a gamma 2, which anti-commutative is H. But certainly the gamma 1, gamma 2 also anti-commute. So everything anti-commute. We have this picture. Then how to construct space of a C2? Well, so we can choose gamma 1, gamma 2 to be the following. So here, let me just so gamma 1 is a sigma x cross I, and gamma 2 is a sigma y cross I, and then this h, the h is became sigma z cross I, and so certainly the sigma z would anti-commute with both x and y, and x, y anti-commute with each other, so everything is fine. And but then we can do this rotation of the rotation is a sigma 0 cross this n by n matrix, and sigma 0 cross the diagonal of n by n matrix. Okay. Here we only have a. I'm sorry, this is very important. Here we have this n1 by n1 minus n2 by n2. This is important. We have this block. Yeah, this one is a block. Okay, this works. And we only have, here has to be sigma 0 because this matrix, this rotation has to keep both invariant. And we have x and y. So this term has to be commuted with both x and y to make this invariant. So this can only be sigma 0. We cannot put a sigma x, sigma y here. Only sigma 0. But the sigma 0 don't do anything. You can see the sigma 0 don't do anything. So again, all we have is a n by n rotation act on this block matrix of I and minus I matrix. This is very similar to the C0 case. It's not same as this case. So as a result, that C0 equal to C2. They are periodic. Then you can go on. Actually, it turns out that the Cn equal to Cn plus 2. That pi 0 we already discussed is Z. So C0 have a lot of component, but pi 0 of C1 equal to 0. So this describes the connectivity for all this classifying space. So for even one, the connectivity is Z. For the other one, it's just one component. They ask, why you do this? Well, so now let's see. Actually, this result directly gave us the result for higher dimension. So how to classify the higher dimensional gapped phase? We can start with, as I mentioned, we can start with a Dirac point. We can have a gamma I, ki, and sum over k. So here what we do is following. Let's assume we have a Brownian zone, but we have one Dirac point. Okay, and so then we try to open up the gap here. Then different way to open up the gap for Dirac point give us different insulators. We want to classify how many different ways to open the gap for the Dirac point. But for Dirac point, near Dirac point, the Hamiltonian is very simple. It's some gamma matrix times ki, where the gamma matrix have this property that they anti-commute. Okay. Then to gap Dirac point, also very simple. We just add another matrix M, hoping this matrix M would gap it, would make this Dirac nodes into something quadratic. But this is a little tricky. If M is identity, they will commute with all the gamma. And such identity M only shift Fermi energy. You already have this. If you add M, this Fermi energy from here to here, just shift, you get a pocket. You don't gap it. In order for M to gap a Dirac fermion, it's very important to have a condition where gamma I commute with M. And that's it. So we have a system of gamma I which commute with each other. And the mass matrix with the gap Dirac fermion has to be a matrix commute with gamma I, all of them. And the eigenvalue of M matrix has to be non-zero, so that we have a gap. And so this M is exactly H we consider over there. Classifying this kind of M is like classifying H over there. So the space for the mass matrix which can gap Dirac fermion is exactly what we calculate the CD in D dimension. That's the space of a mass matrix which can gap Dirac fermion. It's a classifying space we just calculated a moment ago. Then we say that whether this space have a different component or not different component, and etc. And that's give you a class of a gapped face or insulator. And that's it. So it's pretty simple. The first we have this very weird way overkill for 0 dimension. And then we have this mysterious generalization from C0 to C1, C2 by using this anti-commuting property. And now it's no longer so mysterious because in the Dirac fermion, to gap Dirac fermion, when the mass matrix happen to satisfy those anti-commuting property. So therefore, this CD, this abstract mathematical space we studied, actually is correspond to the space of a mass matrix which are capable of gapping Dirac nodes. And once we know the topology of the space, then we know how many different ways which are not connected, how many not connected ways to gap a Dirac fermion. The result is this. For the even dimension, the different way to gap out Dirac fermion is labeled by Z. In odd dimension, they're all connected. So there's no new class in odd dimension. But in every even dimension, we have a Z class. And the chain insulator we studied a moment ago is an example for 2 dimension. So next non-trivial example will be the 4 dimension. So in 4 dimension, we also have this class of something similar to a chain insulator. At the 6 dimension, we have a etc. Yeah. And yes.
So is it in plus 2?
Hmm?
Is it meant to be in plus 2 in the box?
No, I'm sorry. Yeah, I'm totally wrong here. In plus 2, yes. They skip 2,
This also a type.
And
M minus M gamma. It's on the right level. The others M gamma minus M gamma. And in the right side. Right side. Yeah, right side.
what?
And commuting with M is M gamma. Just switch one M with a gamma.
Oh yeah, this will be on this side. Yeah. So this way, we obtain a very systematic theory. Okay. And then almost yes, please.
Is this related in any way to like statistics in a
No, because this is a one-body problem. You can see we have a single-body problem. Has nothing to do with the statistics. We just studied the band. But the statistics will come when you try to fill the band. The band is trivial, non-trivial. It has nothing to do with particle. But if you want to fill the band with a fermion, then we get the insulator. If you don't have a boson, such band can never become insulator. And so statistics only happen later when we try to fill the band. But when we study the property of band, our property of this matrix, no statistics, just mathematical probability matrix. A matrix have a gap, how to classify them. And here I just want to make one last comment is that here we consider the Hermitian matrix. This is the Hermitian matrix. And there is a similar problem associated with the anti-symmetric matrix, real anti-symmetric matrix. So somehow, this real anti-symmetric matrix is more general. And there's another class of a real anti-symmetric matrix. You can do the similar thing for real anti-symmetric matrix. And that kind of theory will become a theory which classify the things like topological insulator or topological superconductor. So there's a whole class for the real anti-symmetric matrix and how to classify the gapped real anti-symmetric matrix. There's a theory. And there the periodicity is now 2. They have similar classifying space. I forgot how that name it. Look on the D. The periodicity is 8. So it's much richer. So when you increase dimension, the repeat will go to 8 dimension. Yes?
With respect to Jason's question, the fact that you're somehow requiring that your gamma matrix is anti-commute with the Hamiltonian, isn't that like...
No, not Hamiltonian. This is just matrix. But this is really about this gap in the Dirac nodes. So over there, just mathematics. The physics is that we want to classify mass matrix. In order for mass matrix to gap the Dirac point, the mass matrix needs to be anti-commutative with gamma. So then that becomes mass matrix. So this is a mathematical requirement. It has nothing to do with statistics. It's really just a single body or matrix. In order to make a matrix gapped, we need this anti-commute. But this anti-commuting property is not statistically related. Just try to gap the Dirac point. Yeah. Yes?
So how does the non-trivial numbers of the connection, the pi function, related to Chern insulator or something you said?
No, this is okay, this is very interesting. So remember this pi 0 C2 equal to Z. So that means in 2 dimension, there's the class of gapped Hamiltonian is a Z. And this Z directly corresponds to Chern number for the total. This is total Chern number below the gap. There's a total Chern number, C total. This total Chern number below the gap is correspond to this Z. Yeah. And so this is thank you for the question. Really, the total Chern number below the gap correspond to this integer Z, which classify different insulator. Yeah. Other questions? Okay, I think I'm pretty late, so I'll stop here.